All right, let's start today's class. So far we have talked about, well, in the first lecture we talked about, making efficient neural network. We have pruning quantization, and the other is this knowledge distillation, right? We showed you, if you still remember, on one of the slides we have this the comparison of after you applying pruning quantization and knowledge distillation, and then like combine everything together. So today we are going to talk about knowledge distillation, this the other model compression technique. So we are going to talk about knowledge distillation, the details. We're going to talk about some different tasks, and finally we are going to talk about a different type of knowledge distillation, is a network augmentation. All right, so let's start. So well, this one just shows you, the comparison of large hardware and small hardware. And so we can see that both the computation and the memory are very different. And to make everything work for this tiny ML, like we need all the tools we can get our hands on. So this. What is this trying to show? So this one is trying to show that the tiny models on the fit large data set. So even you do have like a large data set, all these small networks are just too small. They can't memorize all the knowledge, basically. Even you train those small networks fully, the accuracy is still far from the large network. So the idea of knowledge distillation is that we are going to have a teacher network and a student network. So instead of like what we did for pruning and quantization is that like we directly pruned or quantized the original model. Now we're trying to have a smaller network and try to use this smaller network to learn from this larger network. So that's the key idea. And we are going to have, so how do we make the student network learn from the teacher network? We are going to have like this distillation laws. So we are going to talk about it in detail. So when we are trying to teach a student network, the most intuitive way to do this is to match the prediction probabilities between the teacher and the student, right? So if you remember like how we are doing this, when you are doing this classification task, like we have a cat. So what happens is that like we are going to, after you go through this convolution, you go through the fully connect layer, you have this logics, right? So logics represent like how likely it is it's a cat or dog. And then you go through this softmax to have this probability distribution. When you are doing softmax, essentially you are doing this, right? So e power to 5 plus e power to 1 and divided by this, right? So and this same thing for this logic. So that gives you this distribution of 0.982, 0.017, then the network says, oh, it's much more likely to be a cat, right? So but if it's a smaller neural network, because you are not able to learn so well, you might have have logics like this, so 3 and 2. And if you do this softmax, you are going to end up with this probability. So still the network still thinks it's a cat. It's more likely to be a cat, but the probability distribution is different from this one. So it has a lower confidence. Make sense? So when we are trying to teach a new student network from the teacher's network, we are trying to boost the student's confidence to more likely to match what the teacher says. Okay, so that's what kind of the main idea of knowledge distillation. So how do we increase the probability of this one, reduce the probability of this one? So one thing that I forgot to add is that like when we are doing the softmax, usually there's a temperature, something called temperature, this T, so which is divided like inside of this exponent, like 5 divided by T, and here, if the temperature is 10, like it's 5 divided by 10. So if the temperature is high, then like the probability will be more smoothed out. If it's low, well, by default, the temperature is 1. Okay, so just keep that in mind, and we will come back to that. So formally, the knowledge distillation is defined as the neural networks typically use the softmax function to generate these logits to class probability of this using this softmax function. Here are I equals to, all 0 to C minus 1. C is the total number of classes. T is the temperature, which is normally set to 1. Okay? And the goal of knowledge distillation is to align the class probability distribution from the teacher and the student networks. All right. So this this probability matching is just one way of kind of boosted the confidence of the student. Okay, so there are like people like try the different ways to match the capability and see how to better teach the student network, because eventually we care about the accuracy, right? So next we will talk about what to match. Is it like only match the final distribution, the final probability distribution, or like can we match something else to make the student better? So there are different like researchers that they are trying different ways to do the matching. The first way, of course, is this output logics. That's pretty much what we just did. So we are trying to match the logic distribution, and this is a student model, this is a teacher model. So we want to match their probability distribution. So one way to make sure they'll match is this using this cross entropy loss. Another is using this L1 loss. So cross entropy loss essentially is trying to, so when you have this the prediction distribution, you are trying to maximize the similarity of these two probability. For L2 loss, essentially it's this Euclid distance. What you did is simply subtract each vector and using the square, add all the square together, right? So that's the L2 loss. So either way, we can use this loss to train these two networks, trying to make sure like these two network, the distillation loss is minimized. Okay. So and on the other hand, like when the student is trying to do the prediction, we also sometimes we do have the still have the grounded truth, right? So we can have this classification loss. So typically, we are going to use both the classification loss as well as the distillation loss together to try to boost the accuracy of the student. Okay, so I don't have the equation here, but later we are going to show you some of these examples how usually it's simply you are adding the distillation loss with the classification loss. Okay, so where the classification loss, you are trying to minimize the error between the student prediction and the grounded truth, right? Whereas the distillation loss, you are trying to minimize the error between the teacher and the student, and you add them together. So when you are doing the training, you are minimizing this whole total loss. It's trying to minimize both the classification as well as the distillation loss. All right, so next, what about not matching the output logics? Instead, we just match the intermediate weights. Okay, so let's see what it is. So if you look at these two networks, we have so many layers. One idea is that can we just make sure like all these layers, their weights are as close as possible, right? So that's another way of defining this distillation loss. And in order to define this, and how do you define they are close to each other, right? So there are different ways to define this loss. So if you look at this, well, if you want to measure the distance between two matrices or like two vectors, right? There are a lot of ways to measure the distance. L1 loss, essentially you're just doing the subtraction. L2 loss, essentially you are doing the subtraction and the square, right? And then add them together. So there are many different ways to defining the distillation loss here. So one way is presented here as the, what is this? Here it's using the L2 loss. Essentially, you are doing subtraction and square and then add them together. But one thing to notice, before you do that, one thing to notice that the weight of this, the weight shape in this teacher network may be different than the weight shape of the student, because the student is smaller, right? So you have to add this fully connected layer kind of to project from lower dimension to higher dimension. And then you do the L2 loss to try to minimize them. Okay. So well, intermediate weights is one way. What about intermediate features? Okay, so that's different. So the weights are the weights, between these two layers, all these weight matrices, right? The feature map is the output of these layers. Okay, so that's another idea, right? So the intuition is that the teacher and the student should have similar feature distribution, not just output probability distribution. So you can, again, like if you have all the feature maps, then you can use the define your own loss. Again, this can be L1, L2, whatever similarity you want to measure between two matrices. All right. So another idea is to imagine the gradients. So what is the gradient? So gradients of the feature maps are used to characterize the attention of the DNNs. So the attention of a CNN feature map X is defined as this. So it's the L2, the derivative from the loss to the derivative to the X. So what that essentially means that it's the slope on this variable X right? So what that means is that if this attention is large, means that a small change for the X is going to lead to a large change. Even a small change in the X will lead to a large change in the loss function. Does that make sense? That's when the attention is large. Therefore, we say like the network probably is putting more attention on this I and the J. So therefore, you can actually calculate this derivative for the X's, right? So then like you are trying to match these two map. Okay, and again, essentially these two are just two matrices, right? You can again define whatever loss you want on these two attention map. Okay, so these are just different ways people are trying to attack the what's the best way to teach, different ways to teach, and they may have different accuracy for for different networks. So it's more like depends on what your network is. Different methods might work better. Right. So so this one basically I want to show you that the performance models have similar attention maps. So this one is this NIN, this is a network. Then I have a ResNet 34 and a ResNet 101. This is trying to see like how similar the attention maps are. You can see that while this NIR only has a 62% of accuracy, these two are 73 and 77. So you can see that the attention map of these two ResNets, they are more similar. So for example, one way, like if you want to improve the accuracy of NIN, one way is that you can define the attention map, the distillation loss as the attention map difference similarity between like this one and this one, right? And this one, and use that as a loss to make the attention map as similar as possible, kind of to boost the accuracy of this network. So essentially that's the idea. So that's the attention map. Another thing is the sparsity pattern. So what is this sparsity pattern? So the intuition is that like the teacher and the student networks should have similar sparsity attention after redo function. So we are going through convolution, and every time we go into redo, right? So in the redo, essentially you are make everything 0 and 1s. So a neuron is activated after redo if the value is larger than 0. So defined as this. So you are trying to match the attention pattern of these two. So if you look at this, when people are trying to, doing the distillation, essentially we are looking at different stage of the network, right? We are looking at the weight. We are looking at the activation. We are looking at the attention map. We are looking at the ReLU results and trying to make them like similar, basically. And this is sparsity pattern. Essentially, it's a 0, 1 matrix vector, right? And then you can define the loss to make them like more similar to each other. Okay, so the final one is a little bit more interesting. This is relational information. So what is that? Let's take a look at this figure. So the teacher model here has 32 layer. This is the 14 layer student network. Okay, so what it does is that like if you look at this residual models, so like module, so you have like 5, 5, 5, 2, 2, 2. What it does is that it's trying to use the inner product to extract relational information for both student and the teacher networks. What is this relational information? So essentially, it's so remember when we talk about this residual module, we have all these different channels, right? So the relationship. So basically, what it does is that it's taking one channel I and another channel J and doing inner product, and to get one value. So let's say I have 5 channels in this module. Okay, so I have 5 channels of the weight matrix. Okay, and then like for channel, I'm going to do a inner product for channel 1 and 2, and get one value, right? And then like I got another 1 and 3, 1 and 4, and 1, 5, and so 1, 2, 3, 4, 5, and then like I'm going to do 2, 3, 2, 4, 2, 5. Okay, so and then like 5, 4, 5, 2. So in this way, you basically get a one single matrix, which kind of capture the similarity of all these channels. Does that make sense? So and then like it says, well, the similarity of the channels between the teacher and the student, they should be the same, and they call this relational information. Okay, they are trying to make it that matrix from this from these inner products of these channels to be as similar as possible. Okay, so and then like they got these two results, G1 and the G1T and the G1S, and define a L2 loss on them, trying to minimize that loss, make the relational matrix as similar as possible. Okay, so that's that. So this one also like trying to this is another paper. Instead of trying to find the relational information within a single input. So remember, like this one is giving the same input. I'm going to get a relational information on this and the relational information on this, right? But this paper is trying to say, oh, if the teacher and the student, the capability, if they are the same, then their relationship they extract for these different inputs should also be similar. So what it does is that they are looking at the relations between the intermediate features from multiple inputs. What that means, if you think about it, basically says, well, if the teacher can know these two, which two birds? Okay, so if the teacher knows that the first bird and the third bird, these two images are more similar, then the student should also be able to extract that similarity between different inputs. That's the idea. So therefore, they are calculating the similarity between the intermediate feature maps across different inputs. And they are trying to make sure the teacher and the student can extract this similarity information across different inputs. Okay, so that's that. So what is this? Right. So this is basically the illustration of that. So if I have multiple inputs x1 to xn, so the teacher will extract like t1 to tn different feature maps, right? And the student also will extract s1 to sn feature maps, right? And then like for each pair, like t1 and the t1 and the t2, I'm going to do a inner product. If I do inner product, I only get one value, right? So every item, I'm doing like a item-wise multiply and then add everything together. So you get one value for each pair of these feature maps. Does that make sense? So you got, and then like you do 1, 2 got one value, right? 1, 3 got one value, and 1, n got one value. Okay, and n1 got one value, n2 got one value, and n got one value, right? So eventually you got one matrix describing the relationships among all these different feature maps across different inputs. Does that make sense? And then we are doing the similar for students. And then like we got these two matrices, okay, and I'm trying to make them their L2 loss as small as possible. Okay, so this is basically teach the student to extract the similarity information across different inputs. And all these methods, they are not, most of them are orthogonal, means that you can apply them all together to see if they are improving the performance. And most time they are. So I think, so I remember there's one paper that's trying to do both, and they show that they can improve the performance. Okay. So that's what to match. Okay. So just recap. We can match the output logics. We can match the intermediate weights. We can match intermediate features, the gradients or the attention map, the sparsity pattern out of the ReLU function. We can match the relational information. Okay. So next, let's talk about this self and online knowledge distillation. So what is a self-distillation? So self-distillation also like published in one of the papers. Usually when we are doing the knowledge distillation, the teacher usually is larger. The teacher's model is larger than the student model, right? So this paper has this really interesting idea of using itself to teach itself. And how to do that? Like, what does that even mean? So when we are training, we go through multiple stages. Okay. So in this first stage, we used all the inputs to train one model, which is the T. So now we have one model with one snapshot of all the weights, right? And the next time, in the next iteration, because I have the older snapshot, right? I'm going to train the new self. Okay, I'm evolving myself. I'm going to train another copy of myself. Does that make sense? But that copy's loss function now is going to be, well, remember, the first time when you are training yourself, the loss function is only the final loss function compared with the grounded truth, right? But now, like in the second iteration or second step, when I'm training this copy as one, I'm going to use my older myself to define a distillation loss as well as the grounded truth, both of them to train the weight of this copy. Does that make sense? And then like I'm going to do this iteratively until k iterative and see how that improves the, so you have multiple snapshots of your own weight. Okay, and every time you are using previous snapshot to teach yourself as well as the grounded truth. So this is so-called like self-distillation. Okay. And finally, because you have so many snapshots and you can do a voting, right? So for a inference, for input, you can have everyone outputs a possibility and do a voting. Let's see what's the majority, let's say like a majority vote. And that's called this ensembling to give you the best accuracy. Yes.
Yeah, so like the reason why is the distillation because we want to maybe shrink the size of the molding.
Right.
But if we use this kind of like a self distillation, I mean, we even have like more parameter size.
Right. So the purpose of this one is to improve the accuracy. So this one is not reducing the size at all. Yeah.
Thank you.
Later, actually, you will see. Later, you will see. Actually, we sometimes we may even increase the size to do knowledge distillation. So reducing the size is just one usage of it. And later you will see like how we can use knowledge distillation for other purposes. Okay. But yes, we are like apparently this one we are increasing multiple copies where we increase the storage overhead, right? But we got better accuracy essentially. So next is this online distillation. So the idea of this is that so we don't have a teacher, okay? So we don't have a teacher that's readily available, okay? So this one basically says, well, if I don't have a teacher available, I can just create like two network, theta 1 and theta 2, and like during the training. Now, essentially, it's very similar to self-distillation, but here the theta 1 and theta 2 they can be the same or they can be different. Okay, so I'm creating two networks, theta 1 and theta 2, and then I'm going to train both of them from scratch. Okay, and during the training, I'm going to minimize the loss, both the prediction loss as well as the distillation loss. Essentially, I'm trying to make the prediction probability distribution as similar as possible. So you can see that we are defining so we are training both the teacher and the student together, and we are adding a distillation objective that minimizes the output distribution of the other party. So it's not necessary to pre-train the teacher. We can train them together, and they can also be the same. Okay. So if they are the same, then it's very similar to the self-distillation, right? So they also find out that like if you do that, essentially, if you think about the main idea here is that like, wow, if one student is not very good at learning from the raw data, then am I having multiple students all learn from the raw data and then ask the student to teach each other? So that's the key idea. Does that make sense? So the self-distillation, it's more like, well, if learn once is not good enough, I'm going to learn multiple times. And I'm both learning from my older self as well as the textbook itself. Okay, so that's kind of so see, a lot of all these research ideas, they came from, your life experience, right? So it's very, and it works. It's just like how you are implementing this in all these networks. Okay. So they show the experiments. So let's just look at this CBAR 10, and let's look at these two columns, this independent and this mutual, deeper mutual learning. So you can see that in all these networks, for this ResNet 32, the mutual learning, it's increasing the accuracy a little bit. Okay. But you can see that like most of them can bump the accuracy up a little bit. But consider the original accuracy is already very high, so that even that small increase, it's something. Okay, so combined. So can we combine all these things together? The answer is yes. So this paper is called "Be Your Own Teacher." So this is also a little bit different, but it's kind of combining everything. So let's look at this figure. So first of all, this network is a multiple exit network. So this is a Panda input. I have a ResNet block 1, and I have an exit from this one, okay? And I'm adding a bottleneck 1 and adding a fully connect layer, have a softmax. I'm going to give you a result, okay? And intuitively, if you have an early exit, it means that like, well, if I'm not going through all these blocks, it means that the capability of my extracting all the information from the raw data is relatively low, right? So that gives you a relatively low accuracy, which is understandable, okay? But it's much faster, right? Because you are not, basically you're skipping all these ResNet blocks, okay? So the accuracy is not good, but acceleration is good, okay? And then the second exit is this. So you have a bottleneck 2, fully connect layer 2, softmax 2. Well, accuracy is a little bit better. Acceleration is slower because now I need to calculate 2 less blocks. Okay. Then I have exit 3 and the final exits. So essentially, this network has a total of 4 exits. Make sense? Okay. Now let's see what does this, where does this distillation come from? So, well, in the forward calculation, when you have the input, well, one possibility is they data all the way to here, give the result, and the other 3 are also, all of them are going to give you the result, right? Their own prediction. And then like it's going to do a lot of different distillation. But instead of like learn from another teacher, the shallow layers is trying to learn from the deep layers. Because intuitively, the deep layers are going through all the stage, going to give you the higher accuracy. And how do we learn? If you look at the gray, let's follow the gray lines. So you can see that it's the gray lines. The gray lines essentially you are trying to use L2 loss to match the feature maps. So the activation feature maps. So and use L2 loss to make sure all these feature maps are aligned across these different exits. Okay, so that's the gray line. And the teal-ish, bluish line here, you are trying to match the, I think the word is a little bit, the label is a little bit off. So the blue line here, you are trying to minimize the KL divergence from the so essentially the blue lines are going to trying to use the grounded truth to train this network. Okay, and finally the green lines are trying to match the output logics with all the prediction probability between all these different exits. Does that make sense? So you're combining like all these feature map alignment, label training, as well as the softmax, is the output logics, the probability alignment, everything together. And let's see how good the result is. Okay, so we don't need to do like all these training. You don't need to do everything together. Right? You can do this different passes, or you can add all these losses into one single loss function to minimize everything. So there are different ways of doing this. So this is the result. Okay, so so the results on this is CFAR 100 shows consistent performance improvement over the baseline. And you can see that by doing all these, this learning. So sometimes you can see that, like for example, for the VGG19, the exit 3 actually giving a higher accuracy than this exit 4. Okay, so what you can do is that essentially you can do a voting. You can do a voting for all these exits got the highest accuracy. So compared to the baseline, which is only the final exit, so this one gives you this 4% of accuracy improvement. Okay. So so they show consistent improvement. Sometimes, for example, like this 48, as I said, like this 68 is even higher than the baseline's final exit, which means that you got less computation because you take the early exit and higher accuracy. Okay, makes sense? So that's self and online distillation. So next let's take some time to talk about to see like how people are using knowledge distillation for some specific tasks. Okay, so far we have been just assuming on classification tasks, right? We have the label, we have all these loss functions. So we can do for other tasks as well. So this is a second, I believe this is object detection. Okay, so this is object detection. So we have the teacher model, we have the student model. So all of them have this detection. Okay, so one way is that like you can this hint is the feature map. So you can align the feature map, use the L2 losses from the teacher and the student. So that's pretty much what we learned for classification tasks. So when you are doing the detection, then you are essentially doing this. Essentially, you are doing this when you are doing the object detection. Essentially, you are doing this label level. Pixel level classification, right? So you want to see which like the face is what you want, and the background is not what you want, right? So you're doing a binary classification for all these different pixels. So you have this weighted cross entropy loss. Does anyone know what is a weighted cross entropy loss? So for a object detection or a segmentation task, what we need to predict essentially is what is the object, which pixels are my objects, right? So we can like say like the face is all 1, the background is all 0. Does that make sense? Does that make sense? Then if you are just using the same loss function for both the background and the object, means that like we will have same penalty when you are predicting wrong for both the object and the background. And then what will happen is that the network will soon find out, oh, usually the background is much larger than the face, usually, right? So the network will gradually soon learn that, oh, I will just predict everything is background. And I will have a very high accuracy because the background has much more pixels than your face. Does that make sense? Which is not what we want, right? So what we did usually for this kind of object detection function, what we did is this weighted cross entropy. Essentially, we are giving a different weight when you are making mistake for face or the background. If you are making a mistake for the face, then we are going to give you a large penalty. Okay, so if you are making a mistake for the background, we'll give you a small penalty. So what that means is that then you can't just predicting everything as background, because if you're predicting all these faces wrong, then your penalty is going to be high, so the loss function will be very, very big. The loss will be very big. Does that make sense? So so that way we kind of do this is called a weighted cross entropy loss. Okay. Interesting, right? So see how the network will like soon learn how to trick you to give you the accuracy. So so that's this weighted cross entropy. You can try to match, the result from the teacher and this. And then I also have like this bounded regression loss. So this is also like this. So this is the classification task. This is a regression task and trying to match the regression loss. Okay, and finally we have this ground truth label to train these two networks. Okay, so that's how you are trying to do for this object detection. So here you can see that when you are trying to match the feature maps, essentially you are doing L2 loss. And the weighted entropy is this. And this is the bounded regression. So for the regression loss, essentially we're exploiting teacher's prediction as the upper bound for the student to achieve. Once the quality of the student surpasses that of the teacher with a certain margin, the loss becomes 0. And finally, we have this ground truth. Well, in this paper, they did one interesting optimization is to convert this bounding box regression to classification problem. So if you are doing this object detection, if you want to do regression, essentially you want to match the bounding box with the grounded truth as much as possible, right? So that computationally, that's more expensive. So they want to convert this regression problem into a more efficient computation problem into a classification problem. What do they do? What they do is like they chop this whole space into this 6x6 cells, okay? And then instead of like I'm trying to compute the overlapping of this bounding box with the grounded truth, I'm going to predict which cell, the 6x6, which only 16 classes, only 16 cells, right? So I want to predicting which cell is likely to be a corner for the box. So that essentially turns this regression problem into a classification problem. I have 36 classes, and I want to predict which cell is the truth. Does that make sense? So they are doing this and find that's more efficient. But the catch is, how many points do you need to determine to actually fix the box? 1 point essentially apparently is not enough, right? 1 point is not enough. At least like you need 2 points, right? So you need to like the left top or the right bottom points, okay? But then that's going to be a 2-class classification problem, not what we learned. So what they did essentially is they are going to predict the left top corner once, and then predict the right bottom once, then two times doing the classification problem, okay? And then that's not it, because then like for every image, you only got 1 point. Every time you only got like 1 point. Either it's left corner or it's the right corner, right? But how do you know that left corner is pairs with this right bottom corner? Does that make sense? Then they need to solve this matching problem, this combining left corner and the right corner problem. So they essentially they are converting this regression into 3 steps: predicting left corner, predicting right corner, predicting combining together. And still, like they show that that's more computationally efficient than calculate the regression problem. Okay. So okay, they didn't show the details, but that's kind of how they did this. This one essentially just shows you how we are matching using the L2 loss to match the. I'm sorry, not L2 loss. This either cross entropy or KL divergence to match the distribution of these two loss probability distribution. Okay. So this is another paper. They're trying to do knowledge distillation for semantic segmentation. Okay. Very similar. First, here's the input. That is the output. Okay, so it's a bottom up. So if you look at the image, what they did is a teacher network and student network, and this pairwise loss. They have this, feature map, and they are doing the pairwise loss function. And this one again can be the similarity, could be L1, L2, whatever you want. Then they are doing the pixel labeling, which is the segmentation, right? So again, for the pixel labeling, they are doing another similarity loss. Okay, so one additional stuff they added to this network is this discrimination network. So this is kind of like this GAN architecture. Not totally, but so what they added is they added a discriminator. So what the discriminator was trained is that it was trained to tell if an image is generated by a teacher or a student. Okay, so if the student is very different from the teacher, then the discriminator can immediately tell the difference. Okay, therefore, and that will forces the student to be as similar as the teacher, so that the discriminator cannot discriminate them, separate them. Okay, and that's done by this loss function over here. So we call like the student, we call this fake embedding, and this is teacher we call this real embedding, and like this network is trying to separate them. Okay, so that's just different things people did. What is this? So this is the knowledge distillation for generative adversarial network. So just in case, like because we did not cover GAN at all, right? So but I hope at least that you have some knowledge. We are actually going to talk about GAN. We are going to talk about when we are going to talk about this content generation. We're going to talk about large language model. We are going to talk about GAN. We are going to talk about distillation. Okay. So, but for now, I'm going to just give you a very high level idea. So in generative adversarial network, essentially, well, the traditional one, that you don't have the teacher and the student. You only have this generation and this discriminator. Okay. So from this image, the original generator is only have one network that's trying to generate an image. Okay. And this image, apparently they want to be, and then I have a discriminator. And the generator is trying to fool the discriminator and to make the discriminator think it's the same as the grounded truth. And the discriminator was trained to tell, the fake image and the real image to separate them, right? So this is kind of this generating and discriminating this whole adversarial process. And eventually, we want to train the generators in such a way that the discriminator can no longer tell if it's from the grounded truth or it's actually an image generated it's a fake image generated by the network. Make sense? So you can have different ways to train these two to make sure this one can generate an image that is very hard for the discriminator to tell. Okay. Then like this paper essentially does is that it's adding this, distillation, knowledge distillation into this GAN network. Okay. So in the generating process, it has a student generator as well as a teacher generator as well as a student generator. Okay. And then like when in the student and the teacher generator, it's also trying to match the inside here. It's trying to match the feature maps using the L2 loss function. Okay, so that's one step. And then it's also trying to match the output of this image with the teacher's image. Okay, and as well as it's trying to match this image with the grounded truth. So now we have three loss functions. One is intermediate feature map. One is between the teacher and student. One is with the grounded truth. Okay. So with all these three different losses, you just add them together and trying to fool the discriminator. Okay. And in doing this, you are going to have a bunch of candidates of student generators, right? And then you pick one out of all these candidates. Make sense? So this is the demo. They show that they can do this in Jettison Savior GPU, kind of a mobile GPU. So you can see that original cycle again give you the 12 frames per second. This one gives you 40 frames per second. And the FID, the index, it's even smaller. So remember, FID is a metric to measure like how similar the image is from the grounded truth. So the smaller, the better. Okay. So so this by doing this cycle again, then you can do. I'm sorry. This again with the knowledge distillation, you can have a faster and more accurate generation. They also show like you can do this interactive image editing because it's fast enough. Okay. So then like we also have this knowledge distillation for natural language processing. So this is the attention head, right? So you have a teacher, you have a student, and they are trying to match the attention map from this teacher and the student. And remember, the attention map is like that heat map, and you can also define L2 loss on them. And this one shows you like this is the teacher. This is a student with attention transfer. This is a student without the attention transfer. So you can see that once you do this, the not attention transfer, the heat map will be, similar between the teacher and the student. We don't have the results. All right, so that is the all the for knowledge distillation for different tasks. So next, finally, I'm going to talk about this network augmentation. So this is the one that I said like sometimes we even like use knowledge distillation to increase the size of the network. And why? Why are we even doing that? There are multiple reasons actually. So first, like let's take a look at this overfitting problem. So overfitting means that like you are training on this data set too much, and you kind of like remember this data set, but you cannot generalize to other data sets. Right? You are using some specific information from this data set, not like a more general image information. Okay. So people what they usually did to avoid overfitting is that doing this data augmentation. Data augmentation, there are a lot of ways. You can add some noises to the image. Okay. You make it more blur, right? That's then you essentially got another image. You can do some rotation. You can do cropping. You can do size, scale in, scale out. Like all this, you can going to get another set of image. They are still the same image. It's just like a little bit different, right? So by doing that, like this data augmentation, trying to avoid this overfitting. Okay, you can also even cut out. You can even mix up, right? So you can do all kinds of different augmentations. Another way to avoid overfitting is trying to remove some of the neurons in the network. So when you are training the network, you are going to skip training some of the network, some of the neurons in some passes. So what that does essentially, if you think about it, what that does is that if I'm like just masking all these neurons during the training, essentially I'm only training a subnetwork of this whole network, right? Right? And then like during this pass, I'm going to mask out these neurons. But during the next pass, I'm going to mask out some other neurons. So in this way, like different passes, you are training a different subset of the subnetworks. Does that make sense? And therefore, during the final inference, you are kind of doing an ensembling of multiple subnetworks. So that to avoid like everyone agrees, like overfitting and agrees on everything. So increase this capability. So this is the purpose of the dropout. Okay. So dropout means like doing some training passes, we are dropping out some of the neurons. We're not training them at all. We're not updating their weights. Okay. But different iteration, different training iterations, we are dropping out different neurons. So we have different ways of dropout. We have a spatial dropout. You are dropping out like this whole channel. You can drop out some blocks. And you can see that actually the dropout and data augmentation, they do improve the accuracy on the validation set. Okay. Because like all the validations that you never see, right? You want your network to be as general as possible. Like any image you see, you should be able to, not just like all the images you learn, right? So you can see that the dropout and all the data augmentation improve the accuracy on the validation data sets because it kind of like not using specific information, using more general image information. Right. So this is for so this one is this ResNet 50. But one interesting thing happened when we are doing this data augmentation and the dropout for this mobile net v2 Tiny, which only has a 32.3 mega max, and this one has 4.1 giga max. Why? The reason is that this network is very small already. Okay, only like 23.5 mega. And for such a small network, if you are doing the data augmentation and you are doing the dropout, it just cannot memorize all this knowledge. Okay, because I'm too small, right? For elementary school kid, if you want to learn, go to learn calculus, it's not gonna work. Make sense? So to solve that problem, we have an idea called this net augmentation. So this one keeps showing you that for this tiny neural network, these are not going to work. So this network augmentation, what it does is that I'm using my original baseline network as the centroid. Okay, this is my center. This is my base. Okay, and I'm going to randomly add some nodes into this. Okay, so you can think about as like I'm going to create a soup self. Okay, I'm going to, because I'm adding more nodes to myself to get a soup network. Make sense? And remember, like here in this example, the super network is a fully connected network, right? So what happens is that I'm going to create a soup self, and I'm going to train myself on the whole data set. Okay. And then but after the training, I'm going to remove all those fake nodes and still just left myself. And that actually improves the accuracy. And then let me give you some little bit more, and then I'm going to explain why this will work. So for this base, I'm going to build an augmented model, okay? And then I would also and of course, when I'm doing the training, I'm going to, when doing the training, I'm going to have the grounded truth loss, right? So that's one loss, and the knowledge distillation loss between the soup self and this myself. Does that make sense? And then one copy probably is not enough. I'm going to create another way of augmentation. So I'm going to create another copy of this soup self, this augmented network. Okay, and I'm going to do this for the loss function again. Okay, and then I am going to create another way of data augmentation. Essentially, based on myself, I'm going to create multiple copies of this soup network. Okay, and then I'm using all those soup network to teach myself. And that actually improves the accuracy of myself. So that's this. So this is kind of knowledge distillation, right? So remember when we talk about self distillation, is that I'm using my old self to teach myself, right? And different iterations. When I'm doing this online distillation, it's more like I'm going to create multiple students and ask the students to teach each other, right? And this network augmentation essentially is that because I am too small, I'm going to create multiple copies of soup self, and then all of them going to learn and then teach me. Interesting, right? So basically, it's kind of like I'm going to create multiple teaching assistants, which are all better than me. And then I'm going to ask them or teach after they learn, then they teach me. Does that make sense? So that's kind of the idea. But this kind of gives you, idea of when people are doing research, what they are kind of a logical way of thinking about this, right? So use myself to teach myself, use multiple students and teach each other. and I can find multiple teaching assistants and teach myself. Right? So that's kind of the general idea here. And here it shows like the augmentation do improve the accuracy. So you can see that the accuracy increase. This is for another network. So they find that like this kind of network augmentation works better for smaller network than for like big networks. And this one says, this network augmentation is orthogonal to knowledge distillation. It means that like orthogonal to other knowledge distillation methods. You can still have like you can create multiple. You have multiple teaching assistants. You can also have multiple yourself, right? You can have multiple self can have multiple teaching assistants, and they can all combine together. Okay. It provides better transfer learning performance than knowledge distillation alone. I mean, so it's better transfer learning performance means that like when we are training on this ImageNet data set and we're tested on other data sets and see how the performance are. Okay, so they found out this network augmentation actually performs better on other data sets which were never trained on for this network. This one says it's improve the accuracy, reduce the max, essentially. Okay, so in this lecture, we talk about what is the knowledge distillation, what to match. We talk about self and online distillation. We talk about knowledge distillation for different tasks, and we talked about a very special form of knowledge distillation is network augmentation. Right. So that's all. Let's take a break. Let's take 15 minutes. So let's come back at 7:20.